Hello, we will mention about our engineering design two lessons projects. Our project is selection of hypopnea and upper airway resistance. Our team member is three people. I am Aslan Derse, Recep Fatih Yumuşakdemir, and Mesut Özkan Ertop. And presentation content, we will begin with introduction and continue with problem statement, requirement specifications, data set used in the study, methods and analysis, and final conclusion. Sleep-related breathing disorders such as hypopnea and upper airway resistance syndrome disrupt normal breathing patterns and pose significant health risk. Although PSC is the gold standard for diagnosis, its high cost, time-consuming nature, and inconvenience for patients make alternative solutions necessary. Problem statement. This slide highlights the key challenges associated with PSC, including its cost inconvenience for patients, time-consuming nature, and the requirement for specialized sleep laboratory facilities. This limitation emphasizes the need for more accessible, cost-effective, and efficient diagnostic solutions for sleep-related breathing and disorders, and we made cost analysis, files and resources, like files literature review and conceptual understanding. Resources is access to academic journal expert consultations. And here is our data set. To begin, we collect respiratory and EEG data from the C3A2 channel for 9 different patients, covering the worst demographics. And the signals were sampled at 256 Hz segments into 30-second epochs and processed for detailed analysis. And these epochs allowed us to identify critical intervals where significant amplitude reductions and corresponding energy changes were observed in respiratory signals. And with that, will continue.
Firstly, I will provide a brief overview of each step as shown in the slides. Following that, we will explain each step in detail to better understand the methodology. First, second, and third step K data are shown in the slide. Next. Fourth, fifth, and sixth step K data are shown in the slide. Next. In the first step, respiratory and EEG data were collected. The amplitudes of the respiratory signals were examined. 50% reduction was observed, were identified. Reduction of at least 50% in signal amplitude indicates that the patient may have a hypopnea or upper airway resistance. If no such reduction is observed, the patient is considered healthy. Next. In the second step, we calculate the energy of the respiratory signals. It was observed that the energy of the signal decreased proportionally with the reduction in the respiration. Next. In the third step, we examine the corresponding EEG data for the same intervals where respiratory changes were observed. Arousal events detected in the EEG data were classified as hypopnea, while intervals without arousals were categorized as upper airway resistance. Next. In the fourth step, we calculate the power spectral density. Power spectral density provided detailed insights into energy distribution across different frequency bands. For the normal patient, EEG signal activity is predominantly concreted in the 4 to 8 Hz frequency band as expected as seen in the graph. Normal patient primarily concretes energy in the low frequency range. Next. For the hypopnea patient, the EEG signal exhibits a more balanced energy distribution across medium and high frequency range. This indicates a more irregular and varied frequency activity, which is consistent with the characteristics of hypopnea episodes. Next. Mesut will continue.
As seen in the graph, UR sample epochs exhibit a denser PSD graphs in the 0 to 4 Hz range compared to other conditions. This provides a significant advantage in feature differentiation during model training. Next, CVT is a calculation based on the variation of signals frequency over time, and with the scalogram, we have the opportunity to observe these changes. As a result, we can see how normal epochs separate from others, which serves as a beneficial feature. Next, the most critical distinction is made for normal epochs in CVT calculations. the hypopnesivity as seen in the slide. Next. And UR's epoch as seen in the figure is not beneficial. Next, please. The sensitivity TPR and the specificity TNR are calculated as true positive divided into the sum of the true positives added with false negatives, true negatives divided into the sum of true negatives added with false positives is specificity. The higher these values, the more balanced and accurate the prediction and classification. The confusion matrix demonstrates that this model is robust. Next. As observed in the ROC curve, the closer the model is to the operating point, the better its performance. This provides a high accuracy in separating patient epochs. Next. Using the Kruskal-Wallis and ANOVA estimation methods is crucial for determining the effectiveness of different features. The calculations performed in this study reveals that these two methods commonly identified thermistor sensor data as the most effective features. Thank you.